And so last time we went over a lot of section 44, 45 of neural networks, right? So we showed a little bit like what a neural network is, all different parts. We kind of motivated it from a perceptron, and like, you know, like these different, basically the little building blocks of a neural network and everything. Oh, cool. People are just coming in right now. That's awesome. Yeah, so that's what we did last time. And then we kind of, I don't think we showed, give me a thumbs up. Did we show how to implement in Keras? There was no coding. Okay, we didn't have that. Okay. And then, so let me go ahead and share my screen then, and maybe you guys can tell me too where we left off as well. So I'll go share my screen. I believe is the right one. Yeah, okay, that looks like right. All right, I gotta move my windows. Okay, so last time, this should look familiar if you guys remember from Tuesday. There we go. We talked about a perceptron, so I'm just gonna go ahead and maximize this. Someone send a message? No. We talked about the perceptron, basically kind of putting it together where it's basically a linear combination and we have some activation in there. Did we talk about activation functions? Give me a thumbs up if we showed you different, okay, good. I want to make sure. I kind of showed you a little bit like how you can create this different functionality based on the different weights and biases for those numbers. So basically, by adjusting those weights and biases, we can allow a similar architecture have different effects. And that's the real power of a neural network, is that by basically adjusting those weights and biases, we can actually create these new functionality. Okay. We talked about how like you can think of it like hidden layers, like latent features. I talked about different parts. So we have our layers. So we're saying like, you know, we talk about the input layer, the output layer, and then layers in between are hidden layers. And those are the hidden layers are building up that extra complexity. We talked about activation functions. And what was the activation function? I said that would probably be your default one. Does anyone remember?
ReLU?
Yeah, ReLU, right? I think pronounce ReLU, right? But yeah, and then what was the one that you probably shouldn't ever use, at least when you're doing this in production or anything like that? Started with an S.
Sigmoid?
Sigmoid, yeah. The sigmoid activation function, which looks like a logistic curve, can kind of considered like old school in the sense that it used to be used a lot, and now we just find that it's just not as useful. There's a lot better activation functions. Usually ReLU is a pretty go-to one, or a good go-to one. We talked about some other hyperparameters, just mentioning it really quickly. We'll talk about those today. I mentioned backpropagation, and then I talked about watching that video series from 3 Blue, 1 Brown. Kind of thumbs up, who by chance was able to watch that series? Okay, I see a thumbs up. Okay, do you guys know what I'm talking about though? Okay, good. So even if you haven't watched it, definitely go watch it through. I think it does a great job and like visually explaining. There's not too much of like the mathematics like focus. It's a focus on the conceptual parts of the neural network, but conceptual in a way that I think is useful, that when you learn the mathematics, it's understood like, okay, that's how they kind of relate together. 3 Blue, 1 Brown does a really great job of doing that. And it's just it's about just about an hour, which seems kind of long, but think about, you know, our study group's about an hour, and you can just watch and just play it through. If you want to, you could speed it up, skip through parts and all that stuff. Okay. So did I mention about bringing in more complexity? So we talked about how we can use like a simple, you know, linear function to like separate things out. And as we get more complex patterns in here, we can basically add more layers, hidden layers, to make more complex, to find more complex patterns. And so this is when I think I mentioned about this playground TensorFlow. So I'm going to click onto this website here. Does this look familiar to you guys? Like we very briefly like saw this at the end, I think. Is that right? Okay, see a nod. Okay, so this actually shows a lot. Like for example, if you have input and you have your output here, your goal would be for any data set, right, for classification at least, is to basically you want to classify it as saying, is it in this group or that group? You know, you might have multiple groups. In this case, we have two classes, blue and orange. And you can see there are different sets. For example, this data set is probably really simple, right? So if I'm starting off with a very, very simple neural network, I'm going to go ahead and just go. Oh, I need one hidden layer. Well, okay, if I have it simply as this part, these two right here are basically kind of like its first neurons, and essentially saying in the feature, is it on the left side or is it on the right side, or is it above or below? And these are different hyperparameters. You can see your tanh, ReLU. We can add regularization terms, which we'll talk about today. And then I go ahead and run this. And what's going to happen, I can like step through each one. So if you notice I click one here, what happened is that, I'm going to restart that just to show you guys. You can see like this weight here is negative 0.32, negative 0.12. I'm going to set it off at just randomly at like 0.5. And I'm going to set this one to 0.5. And just to kind of show you guys a little bit like what the weights do as they kind of evolve. And it's actually probably going to do a pretty decent job. So I'm actually going to make this negative 0.05 just to make things a little bit different. Okay, so you can see here like the weights on this, like on the actual line here. And so if I go one step forward, what's going to happen, we're going to push the data through and say at the end here, well, how well did it classify these points on the test size, right? So you can see here, I'm testing, I'm going to turn this down to 20%. So our test data is about 20% of the total data. So this is going to test on these guys and say, hey, you know, putting all the training thing through here and says, how well does it perform? And so we could take one step forward. You can see here is that it's going to adjust. So you can already see the weights are adjusting from negative 0.5 and 0.5. You can see it start being adjusted. And so what this one epoch did, they passed all of the training data through here, see how well it performed, and said, hey, you didn't perform, you made these mistakes. Let's propagate that error backwards. And that error that we had, adjust essentially through gradient descent, saying what's the most optimal way we should tweak these weights in a certain, like how should we tweak these weights to make it more optimal? Like how do we make it classify better? And you can see here is that this is getting a little better. You can see, well, actually, no, it's not that much better. It's the same thing. Basically, it's classifying it the wrong way. So I can keep doing these steps forward, and you'll see on this graph right here is the graph of the loss. So notice this is the test loss right here and the training loss. The training loss, right, should be lower because we're training on top of that. And our test loss, think of that validation, is seeing how well it performs. So you can see as I do more and more epochs, you can see that part going through, and you can see what I love about this visualization. You can see this kind of neuron kind of change shape, or like not just shape, but like the way it defines its linear boundary. So you can see here is that we had something very simple. These don't change because those are our features. And this thing right here is kind of creating like a super feature, right? It's combining these features with certain weights to create a more complex, you know, separator. In this case, it's just a straight line, but you can see already pretty good. And I can see if I keep going forward, you can see it gets better and better. And basically at this point, training loss and test loss are probably as low as it can. And I can go ahead and press play, and this will keep going. And you can see basically nothing really changes. Like there's not really too much of a change at that point. It's kind of reached that point. And it's just basically this epochs are going forward and backward, forward and backward. Okay, everyone understand how this kind of worked out? Okay, I see some nods. Okay, so this is kind of cool. It's like, okay, cool. Like, but what if we had something more complicated? Like you can see something like this. If I try running this now, I'm just gonna let it go through. You can see that there's just not enough features for us to really create this. This is when we're getting to the point of underfitting, right? Essentially, no matter how hard this structure is going to try, it's never going to get any better than this, right? We're kind of flatlining here. So what we can do is what happens when we have more complexity in our data set? What would we do? Any suggestions?
Add more layers to it.
Add more layers. That's one thing we can do. So we can add like another layer here. Let's start just add one extra layer, right? And see how well that performs now. And what's cool is we can actually see now is that we'll see that these things get more complicated. Now you note here is that we can probably guess ahead of time that we probably need some more complexity here. We need more neurons in this layer as well, right? So I'm going to add a couple neurons here. And this allows us, I'm going to reset this. And you can see this allows us with kind of like new features. For example, this feature is kind of like a diagonal line where the top left is blue. This is a diagonal line in a different direction where the top right is blue. And this one's kind of similar to the very first neuron. Okay, so now we're going to add new complexity. And note the second layer here is going to use these different features together to create a more complex thing. So you can see here already is that this is, I don't know if you guys can see that too well, but on kind of like this corner, or not corner, triangle is kind of blue on the bottom there. And then here's kind of like the opposite. So this is going to start creating new, more complex features. So now if I run this, we should see these more complex kind of features going forward. And you can see that training, it's gotten lower, but it's still kind of struggling, right? It's still not quite right. So in this case, maybe we need more like, you know, some more complexity in this case. I'm going to add more of those features in here. And you can see here now we got something that's a lot closer to what's going on. And you can see what's really cool I go ahead and pause this, you can see that these features now, or these kind of like ending neurons, actually have like more complex than just like this simple like line here. And that's the whole idea of like neural networks, is that as you get deeper and deeper, you get more and more complex behavior. Some other things you could possibly have done, right? So let's like go really simple. I have just one hidden network. I'm gonna use one neuron. Like, and we saw this was really bad, right? When we try doing this, it doesn't do very well. One thing that can happen sometimes is having the right features. So for example, there's this feature here, x1 times x2, right? And you can probably already see, it's like, hey, like this is probably gonna be dominating. And you can see these values here. If I go ahead and reset these for just randomly, just kind of making sure, that's fine. They're close enough to like being small. These two weights will probably go to closer to 0, and this weight will probably be stronger because you can see already does such a great job. So if I go ahead and run this guy, you'll see this weight being dominated across everything else. So you can see here is that the weight is pretty much just like the only thing, these are close to 0. You can see slightly negative, but close to 0. In that case, we can see a near perfect part. So sometimes it's actually just picking the right feature can sometimes be different, can help a neural network. But note that we didn't have to necessarily have this feature. By adding some neurons and some more complexity, it was able to do a pretty decent job figuring out all by itself of something that works pretty well. Okay, cool so far? All right, so the last one I want to show is just this really more complex part. And this one you can see it's got quite a spiral in here. If I go and try to run this, we'll see how well it performs. But my guess is that it's just not gonna find that right sweet spot. You can see it's struggling a little bit. It's starting to get more and more trying to get that curve, but you can see it's just not doing well anymore. In this case, if you look at this graph, it's probably closer to overfitting, right? You can see that loss basically bouncing up where the training is very high. So we're gonna go ahead and reset this, and we want some more complexity. So one complexity thing is to add more features. So you can see here, I'm just adding some extra features in here. I'm gonna add another hidden layer and say, okay, let's go ahead and try to run this now. And then hopefully by adding these extra features, more complexity, you can see we're first starting off in the very first layer here, getting more and more complex, right? And then you can see here getting more and more complex. And the whole idea here is that eventually maybe we'd be able to figure this part, but you can obviously that over time, you can see it kind of figuring it out. You can see it slowly kind of figuring this out. And remember, I'm not doing anything in this case. It's like saying, guiding it specifically what to do. And you'll see here is that this actually does a pretty good job. If I go and pause it, you can see besides these like blue points right here, you can see this actually performs really well. You can see, however, it's probably not exact, right? And this is why it's important for us to make sure we have sufficient data that is representative of what we're trying to do. You probably can guess is that if we have a bunch of orange, it would continue in this spiral here. But because there is no like blue right here, you can see there's probably a blue point should go right here. It thinks it's perfectly fine just to cut right through it. So you want to make sure that your data is more representative of like what you would expect it to look like, okay, for your final test. So now you can see it's going to struggle and kind of go through this part. Okay. And I don't know if this is going to perform well by itself. My guess is that one thing you could add is probably this extra feature right here. And maybe add some more complexity in here. But you can see here now all these different weights. Some weights are being used more than others and stuff like this. And so what we'll find in our optimization, which we're going to talk about next, is going to be basically like, how do we make sure, one, that we don't overfit? How do we get to the answer quicker? We converge to this global maximum faster versus like, waiting where we're underfitting essentially for a long time. There's other ways we can do that, because one thing is as we add more complexity, it's going to take more time. Okay, so we'll try one more time going through. But as I kind of let this run through, any questions about what's going on here and how like this neural network is able to combine these features into something more complicated to finally try to do this classification? Pretty good, thumbs up, thumbs down. Okay, I see some sideways. So yeah, hopefully starting from the very simple case, where we just had two blobs next to each other, we could see we don't need a very complicated neural network. And the big thing about neural networks is just understanding that these hidden layers are basically adding more and more complex kind of like ways of looking at the data set. Okay, and you can see here, it's getting there, but it's probably not gonna be great. So
can I ask a question?
Yeah.
So each layer takes the previous layer or the features, if it's the first layer, and kind of combines them with different weights. That's what's happening there?
Yeah, so this weight right here, or this neuron, is basically taking from this feature, this feature, this feature, this feature, this feature, this feature, and all getting fed into here, but all with different like weights of like how much it should incorporate that into this neuron. And so you can see there is that we have a bunch of different ways. You're only using the same inputs, but they're combining them in different ways to create these different kind of overall features. Then as we get into another layer, they're using these kind of features as inputs and going forward and stuff like that. Okay, cool. All right, so anyway, something to kind of play around with and stuff like that too, to kind of see what things work well. I think it's a great visual one. You probably wouldn't want to program on this directly, like, but I think this kind of can give you a little bit of like hint of like what is visually going on and what like different hyperparameters you can tune and stuff like this. So you can see here, it pretty much converged to the best it could do. But you can see again, is that we have this biasness data where we have this missing spot where it's pretty close, but like you can actually see it's pretty much exactly what it should be. But because of that data set, it's not going to do well. And you can see if I can actually show this test data set, you can see that's what it really should look like. Okay, cool. So I'd strongly recommend just kind of playing around with this, kind of give you a good feel for like seeing how neural networks work. But ideally what we want to do is be able to code this and program it like how we have done in the past. So we're going to show a Keras implementation of actually performing these, you know, kind of like creating this neural network. All right. So this is going to be close to maybe like what the lab is. I actually took most of this code, I think, from this post from keras.io. Is that right? Maybe not. Okay, well, you can check out the documentation. So we're going to build it with Keras, which is basically an API to allow us, kind of like how we use Pandas. It basically makes it so we don't have to code it from scratch, right? And note that I do use from TensorFlow just because my computer has TensorFlow installed. It's another package. But what's nice is that TensorFlow actually has Keras installed internally in it. So I can just go ahead and pull out Keras. So for example, if you just replace this with import Keras, this would work. It would effectively be the same thing. Okay. So first thing I'm going to do is just import basically my package that I need. In this case, what is taking so long? Good, got me worried there for a second. So then what I'm going to do here is I'm actually going to import certain parts for the neural network. I'm going to import models, which allows me to make, you know, a neural network, or layers, which will allow us to make hidden layers, input layers, output layers. And also put optimizers in here, which we'll talk about next when we talk about section 46. But just know that basically it's another thing to help us speed up along, you know, make sure we don't overfit and also make sure we get to the right answer quicker than later, okay? And so what I'm gonna do here, I'm gonna use the iris data set. So don't worry too much about this. This is kind of just splitting it up into, we've seen the iris data set a few times now. I'm just splitting up into its train and test splits. I'm also putting into validation as well. So that way I can make sure I can do validation instead of just keeping just my training set, right? So don't worry too much about processing that data. Then it's actually creating the neural network. So this is actually me creating the architecture of the neural network of what it looks like. I'm not going to train it yet. I'm just going to create like what all the parts are going to look or be. Okay. So oops. I'm going to run this guy sequential. Right? So sequential just means that it's going to run forward like this. There are other models that are not going to use sequential, like sequence to sequence models and stuff like this, but sequential for the most part is what you were thinking about when you think about neural network. So this allows me to create this model here, right? So it's going to be sequential. So it's going to expect these different layers. And then what I can do is actually build up this network with dense layers. So when we say a dense layer, that basically means like that drawing of like what I've showed, like different neurons. And so each time I do model.add, that's adding a layer. So you can kind of imagine like I'm stacking the model on top, right? Like a new layer, a new layer, a new layer. And so the first thing I can do is say, okay, I take my model, which I already have here, right? It's basically emptiness. I add my dense layer, which is dense here, 30 units, which just means I'm going to add 30 neurons in this layer. And then the activation for each of those neurons are going to be ReLU. So note that you can change it to other activation functions or create your own activation functions if you want. But the point here is that I'm just saying, okay, go ahead and use ReLU for each of these neurons. So what this looks like right here, oh, I should also say, since it's my very first layer, it needs to know what's coming in. So I say, well, okay, in the iris data set, I know there's 4 features. So I'm just putting in 4 here. So that's the input coming forward. So just from this layer right here, what this looks like, if I were to kind of draw it out really quickly, is that we have an input of 4. So we have 1, 2, 3, 4. This is my input layer. And my next layer, there's 30 nodes here. I won't draw all of them. And what's doing now is that it's connecting all of them like this. Okay, so essentially I have this part. You can imagine all of them being connected, right? And all that stuff. So these are all connected, and each part right here is going to be a ReLU activation. So ReLU. Okay, so right now it's only at 2 layers, basically. It's my input layer, my hidden layer here, and then I'm going to do a model.add here, and this is going to be my final layer. So the iris dataset only has 3 classes, so I'm putting 3 neurons at the end here. 1, 2, 3, like that. These all get connected, right? So these kind of hidden layer, this hidden layer gets connected to the output layer. And note that I put the soft max here for activation. Basically, it's because we should only have a value between 0 and 1. And those values should basically add up to essentially 1. So for example, if it's class 0, class 1, or class 2, the neural network might output essentially for each of these neurons saying, oh, I think it's class 0 with a, let's say, 10% chance. And then class 1, oh, I think that's an 80% chance. And then say class 2, oh, I think that's a 10% chance. So the idea here is that like the neural network says, oh, it's probably class 1 with an 80% chance. And then maybe it's these other 2. But ideally what we'll do is look for the maximum here. But this can also be useful to saying how certain is your neural network in like determining what it should be. Ideally, we want this to be like, if this is the true class, we'd want this to be 1 and these being really close to 0. Okay, and that's what the softmax allows us to do. Basically, it scales it down so we always have a number between 0 and 1. Okay, cool. Everyone follow me so far? Thumbs up, thumbs down? Okay, I see a few thumbs up. I see some other questionable looks. So if you have a question, definitely speak up, right? Note that one thing I have here commented out, I could have added another hidden layer right here, and that would insert this layer right in between here. Okay, so I just comment out, so keep it nice and simple. This nice 2-layer. So I'm going to clear out this guy. Go ahead and run this. Oh yeah, sorry, I have a couple people. Jayla, how about you go first?
So I just want to double check if I'm following. So the last layer, what you're doing now, there is a classification, and the last layer is the classes, like
right.
What would be the output, like the final.
That's right. This is telling us the output of saying, is it class 0, class 1, class 2? If you had regression, you wouldn't have, you would essentially have an input units of 1, and this activation wouldn't actually exist. It would just be a number essentially, and that would be the number that would come out.
Okay. Okay. Cool. Thank you.
No problem. And then I think Bardo, you had a question too?
Yeah. So if you add another layer, it takes the input from the previous one, I guess, right? You don't have to.
That's right, yeah. So you'll notice that I didn't have to put input dim on this layer, or if I ran it with this one, you'll notice that I don't have to put it there. It's implied. Essentially, it's smart enough to know, oh, I know what the previous layer is, so I can connect those parts. The only reason I have to put input dim here is because it's the first layer. It doesn't know what the input's supposed to look like. Cool. Good pointing that out. All right. So I have my model all built, right? I haven't done anything with it. I just built it essentially. And then what I'm going to do, I'm going to compile it. So what this does is all my extra hyperparameters. So in this case, I have, for example, I define what the loss function is, basically saying, how do we determine if the model is doing well or not? So note, typically for categorical or for categorical classification, we're just using categorical cross entropy. Okay, so something that I might have seen before. And then optimizer, just know that I'm putting in something basically for other hyperparameters to allow us to get to the answer quicker. We'll talk about this a little bit later today. And then I have my metrics accuracy. This doesn't actually change anything, but it's useful in the sense that it will kind of output information for us so we know how well the model is performing. So again, this metrics here is not going to actually change how the model learns. It's just going to tell us a little bit of like information as it's being trained. Okay. So I do model compile and says, okay, I have model architecture. Oh, you want those hyperparameters? They flip a bunch of switches, in the background. It's like, okay, cool. And what's nice is that we can actually see with the model.summary, you can actually see what your model looks like. So you can see here, I have a dense layer with 30 inputs or 30 neurons and a second dense layer with 3 outputs. And you can see 150 parameters right here. This is representing saying, you know, each one of these neurons has a, what's it called? It has an input going into it. It has 5 inputs going in. So those 5 inputs are my 4 features, which I said like the input dim4. And then you might say, what's that 5th one, right? Because there's definitely 5. 5 times 30 should be 150. So what's that 5th one? That 5th one is my bias term. So the bias term also has to be adjusted and stuff like that too. So that's why we get 150 parameters, even though there's only 4 features to input. Okay. And then you can see I get my next part here, which is basically our next, our 30 layer deep, or 30 neuron layer is being input to the last layer here and outputs to 3. And so in total, I have 243 basically little dials I can adjust, which are all the weights and biases of the whole system. Okay. Follow me so far? Okay. So again, I'm not really doing anything here. I just want to show you that you can also grab each individual layer. So later on, if you wanted to get that specific layer, note that these are objects. So you can get, for example, this first layer here. And you can see I can actually get that specific one. You can see that's this one right here, that same number. And so what's kind of cool is that when we compile it, for example, we actually initialize it randomly with the weights. So you can see here, if I do .get weights here, this is the first, if I were to count all those out, basically this layer here would basically have 150 parameters, 150 different numbers I can adjust and stuff like this. Well, if I include the biases. So note the biases are set to 0 right now. So note that this will change. I'll keep this up for now. This will change when I actually train it. And note that these weights and biases will all be different after I do the training. Okay, cool. So now we get to actually train the model. We do something with it, right? So we built this model. We say, all right, let's feed it some data and let's try to see if it can figure out stuff. So in this case, I have our model.fit. So we've seen this before, model.fit. I give it its training data. Note this is the inputs, these are the outputs, right? So properly labeled. Epochs, like I said, these are just another hyperparameter saying how long you can run the algorithm. Validation data, so note that I have validation data I defined way up there, but note that you can technically just say, hey, use the training data and then go ahead and do a validation split by defining this like 0.2. Those are 2 different ways you can get your validation data, okay? So if I run this, this is the thing that's going to take a long time. And note that I keep history here so I can reference it later on. So I go ahead and run this guy. And you'll see here, this goes by really quickly, but if it went slower, you can actually see it train the bottom here. And note as we kind of go through each epoch, it tells me what the loss is, the accuracy, and then the validation loss and the validation accuracy. So note that you can see here this accuracy is really like already 100%, which probably means is that it basically is at this point where it can't learn anymore because it thinks it already knows everything. But you can see the validation accuracy has pretty much reached about 84%. So if I actually check this out now, I can check out the weights. So if remember, these were the weights. So we'll just look at this first row. It's negative like 0.13, positive 0.24, and then all zeros down here. If I go ahead and get that first layer of weights, we can see they're different. In this case, oh, it looks like they're not too different. Looks like it actually got about negative 0.11, 0.24, but you'll see all these biases, for example, completely been changed. And if we looked closer, we probably would see these different weights change. Turns out it looks like these first 2 parameters were actually pretty close to what they needed it to be. Okay, cool. All right, any questions on this training part? Okay, so we trained it. You're like, okay, cool. Like, but let's kind of like say, how well did we do? How well did the model do? So we can evaluate this. So in this case, I'm just reading it as a data frame. So note that history basically is a dictionary. So I'm just basically getting the history of this. I'm just making sure I get all of those parts. And you can see here, I can plot out the accuracy and validation accuracy. So note that basically this is showing me in blue here, the accuracy and validation accuracy. Note that this is actually offset by 1. So technically like this accuracy usually should be, that should move back by, or move forward, no, move back by 1 because it's at the end of basically the run. But for this many epochs, it's fine. You can tell that basically the accuracy reached a certain point right here, which you can see in the validation. Accuracy is getting better and better and better, and basically plateaued about right here where I really couldn't get any better. Okay. You can also see validation loss, which is what I typically would look at, and most data scientists or machine learning engineers would look at too. You can see here in blue is our actual loss, or I should say the training loss, And the orange here is our validation loss. And so you want this to be as small as possible to 0. And you can see they start pretty close together and they're both going down, but you can start seeing at a certain point, it's kind of slowing down this descent. It's possible maybe we could keep going through here, but we probably will get into an overfitting territory where essentially this validation loss might become smaller. Note that this is not the best example for neural networks because there's only like about a 500-ish, I think. Maybe it's less than that for iris data. It has less than 1,000 data points. So note that more data will allow us to find more patterns quickly and actually accurately. Okay. But some other ways we can evaluate, we can see the loss metrics. You can see basically these are the exact values of, let's see here, this is, I believe, this is the loss, and this right here is the accuracy for that test. So we take the model, we evaluate it on the test data that it's never seen before, and we see it gets a loss of about 0.325, which is pretty good. It's like about right here, right? So actually it is better than the validation loss. And then we can see the accuracy is about 83%. Okay. Again, you can see here from here, we can actually make a prediction with our model that we trained. We can make predictions with test data. So kind of similar to here, instead of evaluating, we're just making predictions and we can see those classes. So note that basically each of these rows here represent one data point. And these columns are representing, is it class 0? Is it class 1? Is it class 2? So in this case, it's saying it's with 98, like it's like 98% sure that is class 0, right? And you can see the second point is class 0 here. And this one right here, it's a little less certain, but it's pretty sure it's class 1. So you can start looking a little bit like how confident. For example, this data point right here, you can see even though it decided that it's going to be class 2, the numbers are really close together. So it's a lot less certain on this data point. Okay, makes sense? What we're looking at? Cool. So ideally it's like, well, we don't really like, you know, we might care about this, but like we want to know is like, what did you predict it to be? So you can actually do this argmax class, right? Or argmax from NumPy. And this will basically just pull up the argument. Is it the first argument, the second argument, and the third argument? Which one's the most? And that will return to the class. So you'll see the first one will give us 0, 0. This looks like 1, and then 0 again. So 0, 0, 1, 0. And you can see that's what we get, 0, 0, 1, 0. And if I go down to 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, you can see here, this would be predicted to be class 2, which we can see the 6th one is class 2. Okay. So this is kind of how you can make those predictions from here. And note too, we can also get then evaluation, which again, I just did it another way versus just evaluating. I went ahead and just go ahead and said, okay, what predictions are equal to the NumPy argmax? So basically what things are correct here and divide it by the full size of the predictions. And we can see 83%, which is what we saw at the evaluation part. Okay, cool. Any questions at all on this evaluation part? Pretty cool. Okay. Note that we can save the model for later. So this is something the curriculum doesn't really show. But let's say you've trained this model and you're like, hey, I want to use this model later on. You can go ahead and save this, do model.save. And typically we do a .h5 file, basically just a file format. And this will save the full model in its weights. So what you can do then is you can go ahead and run this guy. Or I'll show you, yeah, I'll go ahead and run this guy. And this will actually save it if I go ahead and go to neural networks. Let's go ahead. You'll see, there it is. You can see it just a few seconds ago. So we actually have this model here. And so we can actually keep this model and then you can use that for deployment, send this out to someone else, use it for later on, you know, whatever. Because when you close this notebook right here, your model's going to be gone. You can't do anything with it, right? You're going to have to retrain the whole thing in order to get any information from it. So we can save the model and then later on actually load the model with this code right here. We say keras.models.load model. This will actually load the model as if we had it this whole time. So this is really useful, like when you come back to it later on. And this way too, you can also keep multiple models and, you know, play around with them and see what they do. Okay. Sound pretty cool?
So when you load the model after you saved it, can you feed again to different data or use like different input to make new predictions and that kind of stuff?
Yeah, so for example, this model.summary, right, you can see this is what it looks like, right? I can have this loaded model right here. When I load this model, let's go ahead and load it. I can now do all the same stuff. Oops, I have to actually make this model. Loaded model is the same thing. In fact, I can go ahead and say, for example, let's do this, sorry. If I do this, for example, the predictions, but instead I do it for my loaded model, I can do the same thing. So here you go. You can see this will give me all the different classes and everything like that. Does that make sense? So you can treat it as if like you ran the code already. Okay. And you can see here. Oh, I forgot to put the axis. So you can see your different parts. So one thing I'll show you real quick then is that, remember that I have this put in here. Let's say I do a new model later on, right? So let's say I go ahead and adjust this model and I change it to having this many layers. Note that I have to run this model over again, otherwise it's gonna add new layers. So if I go ahead and run this guy again, note that summary, note that it has an extra couple layers because it basically just added it on. So if I wanted to redo this, I have to run this guy so it overwrites model. Now if I run this, it'll have 1, 2, 3. We'll have 2 hidden layers and then input and output layer. Run this guy, run this, and now you can see here, for example, I have more parameters to train. So let's say you try this out, like, okay, cool. Like, let me go ahead and train it. I'm gonna train it for 1500 epochs, right? So you can see here, it's going by pretty quickly. It might take like a couple seconds. It's a pretty small data set, so I think it'll go by pretty quick. And you can see it's basically generating all those on the bottom. And so once this is fully trained, I can then actually check it out and compare it with my previous model. So you can see here, validation actually about 87%. It looks like that's pretty similar. So then I can say, okay, let me go ahead and check out this model. You can see, for example, how well it performed, just like I did before. So you can see here, for example, there seems to be a little bit of overfitting right here. It's like, okay, cool. Like, and I can do all these different things. I can see how the different classes for that model, and you can see how it performed. And you can actually compare it with my loaded model, because my loaded model, remember, hasn't changed. If I look at my loaded model, let's just do loaded model dot summary. You can see here, that's my loaded model. My model, though, is going to be a different structure, right? So if I go ahead and say, okay, well, let me just go ahead and check out the classes compared to this one. So let's do model. You can see there'll probably be some differences. So you can see, for example, this guy right here had a difference right here. So you can actually compare these models. You can do different confusion matrices, all because I saved it for later, essentially. So this allows you to basically do comparisons or take this model and I could train it again. So that's a possibility too. Okay. Cool. All right. So that's overall kind of implementation. I wanted to walk you guys through that since, you know, there's kind of a lot of moving parts going through. You can see the code itself to build and actually train this model. It's actually relatively small, right? Like this right here, these 3 cells build up the whole model, right? And then to train it, the only thing to train it was just simply running this guy right here. So really like 4 small cells were able to train it, but the rest of it then becomes like, okay, now that you trained it, what do you do with it? You know, how do you deal with it? Okay, cool. Sound good? Yeah. All right, I see some head nods. Any other questions before I move on then? All right, cool.